In the last video, we were talking about the matrix exponential of a 2x2 matrix with complex eigenvalues, a 2x2 real matrix with complex eigenvalues, and we ended up calculating the matrix exponential. And in this video, we're just going to look at some examples of using this matrix exponential. And I'm going to do two examples. The first example is an example that I already did in a previous video. So solve x prime equals -1/2, -1, 1, -1/2 times x. So the way I did this was I found a complex eigenvector and then found the real and imaginary parts and used that. Now, if you think about what we did, that's essentially what this theorem is telling you with the matrix exponential, because P is the matrix whose columns are the real and imaginary parts of the eigenvector that you found. But let's just use the matrix exponential to redo this problem. So first step is to find the complex eigenvalues. So if you find the eigenvalues, you end up getting -1/2 plus or minus I. Well, actually, if you think about that, look at the columns of this matrix. It's the A and the B that you found before. So you could take A to be 1/2 or -1/2 and B to be 1. If you do that, this matrix here is just equal to A, -B, B, A. So therefore, if you call this matrix A, e to the AT is, well, it's this, right? It's e to the little at, so that's e to the -1/2 t, so e to the t over 2, times the matrix whose columns are cosine bt, negative sine bt, so b is 1, so you get cosine t, negative sine t. Second column is sine t, cosine t. So that's going to be e to the negative t over 2 cosine t, e to the negative t over 2 times negative sine t, e to the negative t over 2 sine t, e to the negative t over 2 cosine t. So the general solution is x of t equals c1 times the first column plus c2 times the second column. And that's it. That's the general solution. Now let's look at another example. So this is a second order differential equation. Solve the initial value problem, y double prime plus y prime plus 9.25y equals 0. Y of 0 equals 2, y prime of 0 equals 8. So hopefully this is something that you learned how to solve in the first course on differential equations. You set up the characteristic polynomial. And the way we're going to do it in this video is we're going to use the matrix exponential. So the first step is to turn this homogeneous equation into a system of equations. So the way you do it is you let x1 be y and x2 be y prime. Then this original equation with the y double prime plus y prime plus 9.25y equals 0 can be written as x1 prime equals x2. That just tells you that the derivative of y is y prime. And then x2 prime, that's the second derivative, y double prime, is negative 9.25y, so that's negative 9.25 x1 minus y prime, so minus x2. So now you have this system of equations, and we can write that as a vector is a matrix times a vector. So x prime equals this matrix x. Okay, so this is our matrix A. And so we calculate the characteristic polynomial, so we get r squared plus r. So remember, it's I guess you could use lambda if you want. So lambda squared minus the trace, so 0 minus 1 is negative 1, so it's a plus lambda, and then minus the determinant, so you get 0 minus negative 9.25, that's it's plus the determinant, right? So it's plus 0 minus negative 9.25, so that's plus 37 over 4 equals 0. Now let's find the roots of this to find the eigenvalues. So it's negative b, so negative 1 plus or minus the square root of b squared. So that's 1 minus 4 times a, which is 1, and then c, which is 37 over 4, over 2a, right, which is 2. So it's negative 1 plus or minus the square root of negative 36 over 2, and that is negative 1 plus or minus 6i over 2. So I can write this as negative 1/2 plus or minus 3i. So we're going to have this matrix where your A is going to be negative 1/2 and your B is going to be 3. So we're working with the eigenvalue lambda equals negative 1/2. Let's work with lambda 1, which is negative 1/2 plus 3i. Okay. So now we have to calculate an eigenvector. So we do a minus lambda 1i. That's going to give you, if you calculate a minus lambda 1i, you end up getting this matrix. So now we need a complex eigenvector. So to find a complex eigenvector of this matrix, we know this matrix is not invertible, right? You just need to find one vector in the null space. So you can just take the first row, swap the entries, and stick a minus sign somewhere. So let's write it as 1 and then negative 1/2 plus 3i. Okay, so now we want to calculate the real and imaginary parts. So the real part is going to be u, which is 1 negative 1/2, and then v is going to be the imaginary part, which is 0, 3. So our matrix P is going to be this matrix whose columns are u and v. Let's calculate P inverse. So for a 2 by 2 matrix, it's helpful to remember the formula. So it's 1 divided by the determinant. So the determinant is 3, so 1 over 3 times. And then you swap the A and D terms, so you get 3 and 1 here. And then you keep the B and the C where they are, but you multiply by negative 1. So you get 0 here and 1/2 here. So that's P inverse. Okay, and now let's write down what our C is. Our matrix C is, the first column is A, and then the second column is negative B, and then B, and then A. So A is equal to PCP inverse. So e to the AT, let's see. So e to the AT is just going to be P times C times P inverse. p times e to the ct. So that's e to the negative 1/2 t cosine 3t negative e to the negative t over 2 sine 3t e to the negative t over 2 sine 3t, and then e to the negative t over 2 cosine 3t. So that times p inverse. And you're also given initial conditions. So the initial conditions, if you calculate e to the at and plug in 0, you just get the identity matrix. So it turns out, and I'll leave this as an exercise because I don't want to explain this. I mean, it's pretty easy to see that to calculate the initial, to use the initial values, you can just take this matrix and then multiply it by the matrix whose components are the initial conditions. So x1 of 0, well, that's y of 0, so that's 2, and then x2 of 0 is y prime of 0. So I have to multiply this by 2, 8. So x1 of 0, x2 of 0 equals that. And then, so I have the p and the p inverse, and okay, I'm just going to save the computation. But what you're going to get is you're going to get x1 of t and x2. So, well, x1 is y, right? So you're going to get y of t, and x2 was the derivative. So you actually get the derivative for free. Well, you don't actually need the derivative because the question was asking for y of t. And I'm just going to save you the details, but just trust me that if you calculate this product and multiply it all out, you get that the first component, y of t, is 2 e to the negative t over 2 cosine 3t plus 3 e to the negative t over 2 sine 3t. And that is, in fact, the solution that you get when you use the, when you do it the other way, right? Without using the matrix exponential. When you just use the complex eigenvalues, or if you didn't learn about the complex eigenvalues when you took a first course in differential equations, if you use the e to the alpha t sine beta t, right? E to the alpha t cosine beta t, you end up getting this when you plug in your initial values. So it ends up getting you the same answer. Now, I'm not saying that this is the best way to do it, but I'm just illustrating the technique using the matrix exponential. So what's nice about the matrix exponential is that it allows you to solve any linear system of differential equations with constant coefficients, right? Because it's just the span of the columns of e to the at. And in this video, we just looked at some examples of applying this to the situation when A is a 2 by 2 matrix with complex eigenvalues.